Standard physics says the universe started with a bang, but quantum cosmology suggests something much stranger, that our reality might just be a random mathematical glitch, a temporary fluctuation in a timeless void that could theoretically correct itself and delete us at any moment. Welcome to the scariest math in the universe. This is quantum cosmology. Everything you've ever seen all of it once fits into a space smaller than the period at the end of this sentence. Actually, that's not even close to how small it was. The entire observable universe, which today measures about 93 billion light-years across, was once compressed into something far tinier than a single atom. We're talking about a size so incomprehensibly small that you could fit trillions upon trillions of these early universes on the head of a pin and still have room left over. Now, if that doesn't already break your brain a little bit, consider this next part carefully. At that unimaginably tiny size, the universe wasn't behaving like the solid, predictable reality we experience every day. Instead, it was following a completely different set of rules. Rules so strange and counterintuitive that even the greatest physicists of the 20th century struggled to accept them. These are the rules of quantum mechanics, the physics that governs the behavior of the smallest things in existence. This creates one of the most profound puzzles in all of science. How do you study the biggest thing there is, the entire universe, when it was once smaller than the smallest things we know? How do you understand the birth of everything when the very moment of creation operates according to laws that seem to defy common sense? This is the fundamental challenge that quantum cosmology was born to address. Quantum cosmology sits at the intersection of two great pillars of modern physics. On one side, we have quantum mechanics, which describes the bizarre world of atoms and subatomic particles. On the other side stands cosmology, the study of the universe as a whole, its origin, evolution, and ultimate fate. For most of the 20th century, these two fields lived completely separate lives, like two neighbors who never spoke to each other. Quantum mechanics dealt with things you could hold in a laboratory, while cosmology dealt with things so vast they stretched beyond imagination. But nature doesn't care about the boundaries we draw in our textbooks. When scientists tried to push their understanding back to the very first moments of cosmic history, they discovered something remarkable and troubling. The universe didn't start out large, it started out quantum-sized. This meant that to truly understand the beginning of everything, physicists would have to find a way to merge these two great theories, to create a framework that could describe a universe that was simultaneously everything and almost nothing. Think about the audacity of this endeavor for a moment. We're asking questions about a time when time itself might not have existed as we understand it. We're trying to describe a moment when the entire cosmos existed in a state of quantum uncertainty, where nothing was definite, where the universe itself might have been in multiple states at once. We're attempting to understand how something, in fact, how everything, emerged from what might have been nothing at all. This isn't just abstract philosophy or mathematical games. The questions quantum cosmology asks cut to the heart of human curiosity. Why does the universe exist? Why does it have the properties it has? Why are the laws of physics the way they are and not some other way? Could things have been different? Are there other universes out there, born from the same quantum processes that gave birth to ours? These questions have occupied human minds for thousands of years, but only in the last few decades have we had the scientific tools to approach them rigorously. What makes this field so captivating is that it pushes right up against the boundaries of what science can know. We're not just exploring distant galaxies or studying exotic particles. We're investigating the very ground rules of existence itself. We're asking whether the universe had a true beginning or whether time stretches back eternally in some form. We're wondering if reality is just one possibility that crystallized out of an infinite sea of quantum potential. The story we're about to explore is one of the greatest intellectual adventures in human history. It's a story that involves some of the most brilliant minds who ever lived, grappling with ideas so strange they seem pulled from science fiction. It's a story that takes us from the comfortable world of everyday experience down to the quantum realm, where particles blink in and out of existence, and then zooms out to encompass the entire cosmos. Most remarkably, it's a story that's still being written, with new discoveries and insights emerging regularly. So settle in, because we're about to embark on a journey that spans everything from the infinitely small to the infinitely large, from the first instant of time to the distant future of the cosmos. We're going to explore how the universe might have created itself through quantum processes, how reality itself might have been born from nothing, and what all of this means for the biggest questions humanity has ever asked. Welcome to the strange, beautiful, and utterly fascinating world of quantum cosmology. Part 1. Understanding the two worlds that shouldn't mix. To understand quantum cosmology, we first need to appreciate why it seemed so impossible for so long. We need to understand the two separate worlds of physics that had to be brought together, and why the marriage between them was so difficult to arrange. Let's start by exploring each of these worlds separately, beginning with the strange realm of quantum mechanics. The quantum world is the domain of the very small. When I say very small, I mean atoms, the particles that make up atoms, and even smaller things like quarks and electrons. This is a realm that exists far below what your eyes can see, far below what any optical microscope can reveal. It's a world that operates according to rules that seem to violate everything your everyday experience tells you about how reality works. Imagine you're watching a baseball game. When the pitcher throws the ball, it travels in a nice, predictable arc. If you knew the exact speed, angle, and spin of the ball when it left the pitcher's hand, and if you had a powerful enough computer, you could calculate precisely where that ball would be at every single moment of its flight. The ball is either in one place or another. It has a definite position at each instant. This is how the everyday world works, the world that classical physics describes so well. Now imagine if baseballs followed quantum rules instead. The quantum baseball wouldn't have a single definite path. Until the catcher actually caught it, the ball would somehow exist in multiple places at once, taking every possible path simultaneously. The act of catching it, of observing where it is would force it to choose one specific location. Before that moment of observation, asking where exactly is the ball wouldn't just be a difficult question to answer, it would be a meaningless question. The ball wouldn't have an exact location. It would be smeared out across space in what physicists call a superposition of states. This isn't just weird theorizing. This is actually how electrons and photons and atoms behave. Scientists have proven it with countless experiments. One of the most famous is the double-slit experiment, which has been called the central mystery of quantum mechanics. Here's how it works. Imagine you have a barrier with two narrow slits cut into it. Behind this barrier you have a screen that can detect where particles hit it. Now you fire electrons, one at a time, toward these two slits. Classical physics would predict something simple. Each electron should go through either the left slit or the right slit, and you should see two bright bands on the detector screen, one behind each slit. But that's not what happens. Instead, you see an interference pattern, a series of alternating bright and dark bands. This is the kind of pattern you'd expect if you were dealing with waves, not particles. It's as if each single electron somehow goes through both slits at the same time, interferes with itself, and creates this wave pattern. But here's where it gets truly bizarre. If you try to detect which slit the electron actually goes through by placing a detector at the slits, the interference pattern disappears. The moment you observe which path the electron takes, it stops behaving like a wave and starts behaving like a particle again. This phenomenon reveals something profound about the quantum world. At the quantum level, particles don't have definite properties until you measure them. Before measurement, they exist in a fuzzy state of probability, occupying multiple possibilities simultaneously. The electron isn't taking the left path or the right path before you look. It's somehow taking both paths in superposition. Only when you observe it does it collapse into one definite state. Another key feature of quantum mechanics is uncertainty. There's a fundamental limit to how precisely you can know certain pairs of properties about a quantum particle. The most famous version of this is Heisenberg's uncertainty principle, which states that you cannot simultaneously know both the exact position and the exact momentum of a particle. The more precisely you measure where something is, the less precisely you can know how fast it's moving, and vice versa. This isn't just a limitation of our measuring instruments. It's a fundamental feature of reality itself. At the quantum level, nature itself is uncertain. Quantum mechanics also introduces the idea of quantum fluctuations. Even in completely empty space, what we call a vacuum, quantum fields are constantly bubbling with activity. Pairs of particles and antiparticles are constantly popping into existence out of nothing, existing for the tiniest fraction of a second before annihilating each other and disappearing back into nothingness. This sounds like science fiction, but it's absolutely real. These quantum fluctuations have measurable effects that scientists have verified in laboratories. The quantum world is also fundamentally probabilistic rather than deterministic. In classical physics, if you know the initial conditions of a system perfectly, you can predict its future behavior with certainty. But quantum mechanics doesn't work that way. It can only give you probabilities for different outcomes. You can calculate the probability that an electron will be found in a particular location when you measure it, but you cannot predict with certainty where it will be. Einstein famously objected to this feature of quantum mechanics with his remark that God does not play dice with the universe. But experiments have consistently shown that nature really is probabilistic at its core. Now let's turn to the other side of our story, the world of cosmology. Cosmology is the study of the universe as a whole, its structure, its origin, its evolution, and its eventual fate. While quantum mechanics deals with the tiniest things imaginable, cosmology deals with the biggest, the entire cosmos in all its vastness. The foundation of modern cosmology was laid by Albert Einstein when he published his general theory of relativity in 1915. This theory revolutionized our understanding of gravity, space, and time. Newton had described gravity as a force that pulled objects together across empty space. Einstein proposed something far more radical. He suggested that gravity isn't a force at all, but rather a consequence of the geometry of space-time itself. Think of space-time as a giant rubber sheet stretched out flat. When you place a heavy object like a bowling ball on this sheet, it creates a depression, a curve in the fabric. Now, if you roll a marble nearby, it will curve toward the bowling ball, not because the bowling ball is pulling on it with some mysterious force, but because it's following the curved geometry of the sheet. This is essentially how gravity works in Einstein's view. Massive objects like stars and planets curve the fabric of space-time around them, and other objects move along the curved paths created by this geometry. General relativity makes specific predictions about the large-scale structure and behavior of the universe. In the 1920s, astronomers made a startling discovery that would revolutionize cosmology. Edwin Hubble observed that distant galaxies were moving away from us, and more distant galaxies were moving away faster. The universe wasn't static, as everyone had assumed. It was expanding. If the universe is expanding now, that means it was smaller in the past. If you run the cosmic clock backward, everything gets closer together. The galaxies converge, the universe gets denser and hotter until you reach a point about 13.8 billion years ago, when everything was compressed into an infinitesimally small, infinitely dense, infinitely hot state. This moment of cosmic birth is what we call the Big Bang. The Big Bang theory has been confirmed by multiple independent lines of evidence. We observe the expansion of the universe. We detect the cosmic microwave background radiation, which is the afterglow of the Big Bang still permeating all of space. We observe the abundances of light elements like hydrogen and helium, which match the predictions of Big Bang nucleosynthesis. The evidence is overwhelming that our universe began in a hot, dense state and has been expanding and cooling ever since. But here's where cosmology runs into a profound problem. If you use Einstein's equations to run the clock all the way back to the very beginning, to time equals 0, something troubling happens. The density becomes infinite, The temperature becomes infinite. The curvature of space-time becomes infinite. Everything becomes infinite, and the equations break down completely. This is what mathematicians call a singularity, a point where the mathematical description stops working. Physicists don't like singularities. When your equations produce infinities, it's usually a sign that the theory is being pushed beyond its limits, that it's encountering a regime where it no longer applies. It's like trying to use a road map to navigate the ocean. The map might be perfectly accurate for its intended purpose, but it simply doesn't apply to that domain. For decades, cosmologists lived with this uncomfortable situation. They could describe the universe from a tiny fraction of a second after the Big Bang onward with great precision. But that first instant, the actual moment of creation, remained shrouded in mystery. The singularity blocked their view like a wall. They couldn't see what happened at time zero, or whether time zero even made sense as a concept. This is where the two worlds of quantum mechanics and cosmology finally had to meet. As you trace the universe back toward its beginning, it gets smaller and smaller. Eventually, it becomes so small that quantum effects must become important. At some point in the earliest moments, the universe itself was quantum-sized. At that scale, you can't ignore quantum mechanics anymore. The entire cosmos would have been subject to the strange rules of the quantum world. But here's the problem. Quantum mechanics and general relativity, despite both being spectacularly successful in their respective domains, are fundamentally incompatible in their current forms. They're based on different mathematical structures and make different assumptions about the nature of space, time, and measurement. When you try to apply quantum mechanics to the gravitational field, to quantize gravity itself, you run into severe mathematical difficulties. Physicists have been working for decades on theories of quantum gravity, attempting to find a framework that consistently combines quantum mechanics with general relativity. String theory, loop quantum gravity, and various other approaches have been proposed, each with its own strengths and challenges. We still don't have a complete, experimentally verified theory of quantum gravity, but we've learned enough to start asking meaningful questions about what the early universe might have been like when quantum effects dominated. This brings us to quantum cosmology, the field that attempts to describe the universe when it was in a quantum state. Quantum cosmology asks what happens when you apply quantum principles not just to particles in the universe, but to the universe itself. What does it mean for the entire cosmos to be in a superposition of states? How do you describe a universe that exists in multiple possible configurations simultaneously? What causes the universe to transition from this fuzzy quantum state to the definite classical reality we experience? These questions push physics to its absolute limits. We're trying to describe a situation that has no observer outside the system, because the system is everything that exists. We're attempting to apply measurement concepts in a context where there's nothing external doing the measuring. We're working at the intersection of the smallest and the largest, the quantum and the cosmic, in a regime we can never directly observe or experiment with. Despite these challenges, quantum cosmology has made genuine progress. It has given us new ways to think about the origin of the universe, new possibilities for what might have happened at the beginning, and new insights into why the universe has the properties it does. It has opened up questions about whether there might be other universes beyond our own, whether time itself had a beginning, and how something might emerge from nothing through quantum processes. The marriage of quantum mechanics and cosmology was difficult to arrange, and in many ways the relationship is still being worked out. But it was a necessary union, because the universe doesn't respect the boundaries we draw between different fields of physics. The cosmos started out quantum-sized, and to understand its birth we have no choice but to bring these two great theories together. In the sections ahead, we'll explore what this union has revealed about the origin and nature of everything. Part 2. The Big Bang's Hidden Secret. Now that we understand the two separate worlds that quantum cosmology brings together, let's dive deep into what actually happened at the beginning of the universe. This is where things get truly mind-bending, because we're going to confront the Big Bang's hidden secret, the fact that the standard story of cosmic origins is incomplete in a fundamental way. When most people hear about the Big Bang, they imagine a massive explosion happening at some point in empty space, with matter and energy blasting outward from that point. But this picture is actually misleading in several important ways. The Big Bang wasn't an explosion in space. It was an explosion of space itself. Let me explain what this means. Imagine you have an infinite rubber sheet with dots painted on it at regular intervals. Now imagine that the entire sheet starts stretching uniformly in all directions. Every dot moves away from every other dot, not because the dots themselves are moving through the rubber, but because the rubber between them is expanding. Furthermore, there's no special center point from which the expansion is happening. From the perspective of any dot you pick, all the other dots appear to be moving away from it. Every point looks like the center of the expansion. This is analogous to how the universe expands. Space itself is stretching, carrying galaxies along with it. There's no edge to the universe and no center point where the Big Bang happened. It happened everywhere simultaneously because in the earliest moments, everywhere was the same place, compressed together into an incredibly tiny volume. Let's trace this expansion backward in time and see what we find. Right now, the universe is vast and relatively cold. The average temperature of space is about minus 270 degrees Celsius, just a few degrees above absolute zero. Galaxies are separated by millions or billions of light years of mostly empty space. But it wasn't always this way. Go back 1 billion years, and the universe was smaller and denser. Galaxies were closer together. Go back further to when the universe was just 380,000 years old. At this point, it was so hot and dense that atoms couldn't even exist. Electrons and nuclei bounced around freely in an incredibly hot plasma. The entire universe was opaque, like being inside a glowing fog. This is the era when the cosmic microwave background radiation that we detect today was created. Keep going back. When the universe was just 3 minutes old, it was even hotter, hot enough that even atomic nuclei couldn't survive except for the lightest ones. This was the era of Big Bang nucleosynthesis, when the first hydrogen and helium nuclei were forged in the cosmic furnace. Push back even further to just 1 second after the Big Bang. At this point, the universe was so hot that even protons and neutrons couldn't exist. Instead, the fundamental building blocks of these particles, quarks and gluons, swam freely in an incredibly dense, incredibly hot soup of matter and energy. And we can go back even further to tiny fractions of a second after the beginning. At 1/1,000,000,000th of a second after the Big Bang, the universe was so energetic that all the forces of nature except gravity were unified into a single force. The electromagnetic force, which governs light and electricity, and the weak nuclear force, which governs certain types of radioactive decay, had not yet separated into distinct phenomena. Go back even further to an almost incomprehensibly brief moment called the Planck time, which is about 10 to the negative 43 seconds after the Big Bang. This is the smallest meaningful unit of time in physics. At this scale, quantum effects of gravity become so important that our current theories cannot reliably describe what's happening. And here's where we hit the wall. If we try to push all the way back to time equals 0 using Einstein's equations of general relativity, we encounter the singularity I mentioned earlier. According to classical general relativity, at the moment of the Big Bang, the entire universe was compressed into a single point of zero volume, infinite density, and infinite temperature. Everything that exists today, all the matter and energy in the billions of galaxies we observe, was packed into a mathematical point. This sounds dramatic, but it's also clearly problematic. Infinite density doesn't make physical sense. When our equations produce infinities, it tells us that we're asking questions in a regime where those equations don't apply. It's like dividing by 0 in arithmetic. The operation itself doesn't make sense, and the result is meaningless. The singularity at the beginning of the Big Bang tells us that general relativity, as magnificent as it is for describing the large-scale universe, cannot be the complete story. Something else must take over in those earliest moments. And that something else, physicists believe, involves quantum mechanics. Think about what's happening as we approach the singularity. The universe is getting smaller and smaller. At some point it becomes smaller than an atom, then smaller than a nucleus, then smaller than a proton. Eventually it reaches the Planck length, which is about 10 to the negative 35 meters. This is the scale at which quantum effects of space-time itself become crucial. At this point, the quantum nature of the universe can no longer be ignored. This is where quantum cosmology enters the picture with a radical suggestion. Maybe there was no singularity after all. Maybe the universe didn't actually begin at a single point of infinite density. Maybe quantum effects step in at the Planck scale and prevent the collapse to a true singularity, smoothing things out in a way that classical general relativity cannot describe. One of the most intriguing ideas in quantum cosmology is that the universe might not have had a beginning in the way we usually think about beginnings. In classical physics, time is something that just exists, stretching from the infinite past to the infinite future. But quantum cosmology suggests something stranger. At the very earliest moments, the distinction between time and space might break down. Time itself might emerge from something more fundamental. The physicist Stephen Hawking, along with his colleague James Hartley, proposed an audacious idea in the 1980s called the no-boundary proposal. According to this idea, as you go back in time toward the Big Bang, time gradually transforms into space. Imagine the surface of Earth. As you travel south toward the South Pole, you're moving in a definite direction. But once you reach the South Pole, there's no further south to go. The question, what's south of the South Pole, doesn't make sense, not because there's some barrier there, but because the geometry itself makes the question meaningless. Hawking and Hartley suggested that time might work similarly near the beginning of the universe. As you trace backward toward the Big Bang, time gradually becomes more space-like through a mathematical process called Euclidean time. Eventually, there's no further back to go, not because you hit a wall or a singularity, but because the concept of earlier ceases to have meaning. In this view, asking what came before the Big Bang would be like asking what's north of the North Pole. It's not that there's nothing there, it's that the question itself doesn't apply to that geometry. This idea is both elegant and strange. It suggests that the universe could be finite in time, having existed for a finite duration, yet have no boundary or edge in time, no first moment where things suddenly popped into existence. Time would simply fade into space-like dimensions as you approach what would classically be called the beginning. Another fascinating possibility that quantum cosmology opens up is that the universe might have emerged from literally nothing through a quantum process. Now, when I say nothing, I need to be careful. Physicists mean something very specific by this term, and it's not quite the same as the philosophical concept of absolute nothingness. In quantum field theory, even empty space, a perfect vacuum, isn't truly empty. It's filled with quantum fields that are constantly fluctuating. These fluctuations can occasionally produce pairs of particles and antiparticles that pop into existence briefly before annihilating each other. This happens all the time in the vacuum around you right now, though the particles exist for such brief moments that they don't violate conservation laws. Some physicists have suggested that the entire universe might be an enormous quantum fluctuation, something that tunneled into existence from a state with no classical space-time at all. This process would be governed by the same quantum mechanical principles that allow particles to tunnel through barriers they classically shouldn't be able to cross. The physicist Alexander Vilenkin proposed a scenario where the universe literally tunnels into existence from nothing. In his picture, there's no time before the Big Bang because time itself is created along with space in this quantum tunneling event. The universe simply appears, emerging from the quantum foam, starting out incredibly tiny, perhaps at the Planck scale, and immediately beginning to expand. This raises all sorts of profound questions. If the universe came from nothing, why did it happen? What triggered this quantum creation event? The answer quantum cosmology gives is both simple and deeply unsatisfying to many people. Nothing triggered it. Quantum events are fundamentally probabilistic and don't require causes in the classical sense. In quantum mechanics, things can just happen with certain probabilities. If the probability for the universe to tunnel into existence from nothing is non-zero, then given enough time, though even that concept is problematic here, it will eventually happen. This is where quantum cosmology touches on some of the deepest questions in philosophy. If quantum mechanics allows the universe to create itself from nothing without a cause, what does this mean for the ancient question of why there is something rather than nothing? Some see this as a complete scientific explanation for existence that requires no appeal to anything beyond physical law. Others argue that it merely pushes the question back one level to ask why the laws of quantum mechanics exist and why they have the form they do. There's another crucial development we need to discuss that relates to the very early universe, and that's the theory of cosmic inflation. In the 1980s, physicist Alain Guth proposed that in the very first moments after the Big Bang, perhaps starting at around 10 to the negative 35 seconds, the universe underwent a period of extraordinarily rapid expansion. During this inflationary period, which might have lasted only a tiny fraction of a second, the universe expanded by an enormous factor, perhaps doubling in size every 10 to the negative 37 seconds. This might sound like just a technical detail about the early universe, but inflation actually solves several major problems in cosmology and connects intimately with quantum mechanics. One of the most beautiful aspects of inflation is that it provides a mechanism for generating the tiny density fluctuations that eventually grew into galaxies and galaxy clusters. Here's how it works. Before inflation, the entire observable universe was so small that quantum fluctuations in the energy field driving inflation would have been significant on that scale. These quantum fluctuations, the inevitable uncertainty in the field's value from place to place, got stretched out by the inflationary expansion. As space expanded exponentially fast, these tiny quantum fluctuations were blown up to enormous scales, eventually becoming larger than the observable universe at that time. After inflation ended, these stretched-out quantum fluctuations became classical density variations, regions where the universe was very slightly more or less dense than average. These tiny differences, typically just 1 part in 100,000, were the seeds from which all cosmic structure eventually grew. Over billions of years, gravity amplified these small differences, causing matter to clump together more and more, eventually forming the galaxies, stars, and planets we see today. Think about how remarkable this is. The quantum fluctuations that happened when the entire universe was smaller than an atom, random quantum jitters in an energy field, got magnified to cosmic scales and became the blueprint for all the structure in the universe. The galaxy you live in, the planet beneath your feet, ultimately traces its origin to a quantum fluctuation in the very first moments of cosmic history. In a very real sense, quantum mechanics determined the large-scale structure of the entire universe. We can actually see evidence of these quantum fluctuations. When scientists map the cosmic microwave background radiation, the afterglow of the Big Bang, they see a pattern of tiny temperature variations across the sky. These temperature variations reflect the density variations that existed in the early universe. When we analyze the statistical properties of these variations, they match precisely what we would expect from quantum fluctuations stretched out by inflation. This is one of the most profound confirmations of quantum mechanics operating on cosmic scales. The Big Bang's hidden secret, then, is that the classical description of the Big Bang is incomplete. At the very beginning, quantum effects must have dominated. The universe might not have begun at a true singularity, but rather emerged from some quantum state we don't yet fully understand. It might have tunneled into existence from nothing, or time itself might gradually fade into something space-like as you approach the beginning. And the quantum fluctuations from that earliest moment, amplified by inflation, determine the structure of everything that exists today. This represents a profound shift in how we think about cosmic origins. The beginning of the universe wasn't just a classical explosion that we can describe with Einstein's equations alone. It was a quantum event, governed by the strange rules of quantum mechanics, where uncertainty and probability played fundamental roles. The universe we inhabit is, in some sense, one possible outcome that crystallized from a quantum state of multiple possibilities. We're now ready to explore what that early quantum universe was actually like, what it means for the entire cosmos to exist in a quantum state, and how the universe transitioned from that quantum beginning to the classical reality we experience today. Part 3. When the universe was smaller than your imagination. Let's now journey back to those earliest moments and try to understand what the universe was actually like when it was in a quantum state. This requires us to stretch our imagination to its absolute limits, because we're going to explore a regime that's so far removed from everyday experience that our intuitions will constantly lead us astray. Picture the universe when it was truly tiny, perhaps at the Planck scale of about 10 to the negative 35 meters. To give you some sense of how small this is, the ratio between the Planck length and the size of an atom is far, far greater than the ratio between an atom and the entire observable universe today. We're talking about something incomprehensibly small. At this scale, space itself was not the smooth, continuous fabric we experience in everyday life. Instead, it was a roiling, turbulent quantum foam. Quantum fluctuations of the gravitational field would have been so violent that space-time itself would have had no definite geometry. On scales smaller than the Planck length, the very concepts of distance and direction would break down. Space would be constantly fluctuating, with tiny bubbles of space-time popping in and out of existence, wormholes opening and closing, the whole structure writhing and churning like water boiling at an inconceivable temperature. This quantum foam represents the ultimate limit of what we can meaningfully say about space and time. Below the Planck scale, our current theories simply don't apply. The smooth space-time of general relativity is an approximation that emerges from this underlying quantum chaos, much like the surface of an ocean appears smooth when viewed from space, even though it's made of individual water molecules in constant motion. Now, in this early quantum universe, something truly strange was happening. The entire cosmos existed in what's called a quantum superposition. Remember from our earlier discussion that quantum objects don't have definite properties until they're measured. An electron can be in a superposition of being in multiple locations simultaneously until you observe it. Well, in the very early universe, it wasn't just particles that were in superposition. The entire universe, all of space-time itself, existed in multiple possible states at once. Think about what this means. There wasn't just one geometry of space at that moment. There were countless possible geometries, each with some probability of being the actual geometry. In a sense, all these possible universes existed simultaneously in superposition. The universe was, at the quantum level, a blur of possibilities, not yet having crystallized into one definite reality. This raises a profound question that strikes at the heart of quantum cosmology. In ordinary quantum mechanics, when we measure a particle, the act of measurement causes it to collapse from a superposition of states into one definite state. But when the thing in superposition is the entire universe, what does measurement mean? Who or what is doing the measuring? The universe is everything that exists. There's no external observer standing outside it with measuring devices. This is called the measurement problem in quantum cosmology, and it's one of the deepest puzzles in the field. Different physicists have proposed different solutions. Some argue that we need to think about quantum mechanics in a fundamentally different way when applying it to the universe as a whole. Others suggest that the universe never truly collapses into one definite state, but rather splits into multiple branches, each representing one possible outcome, an idea we'll explore more when we discuss the multiverse. One approach to this problem was developed by the physicists Bryce DeWitt and John Wheeler. They formulated what's called the Wheeler-DeWitt equation, which is essentially the Schrödinger equation of quantum mechanics applied to the universe as a whole. This equation describes how the quantum state of the universe evolves, but it has a peculiar feature. It doesn't explicitly contain time as a variable in the usual way. In ordinary quantum mechanics, the Schrödinger equation tells you how the quantum state of a system changes over time. But the Wheeler-DeWitt equation seems to describe a timeless quantum state of the universe. Time doesn't appear as an external parameter along which the universe evolves. Instead, time emerges from the relationships between different parts of the quantum state. This suggests something profound. At the most fundamental level, the universe might be timeless, and what we experience as time is an emergent phenomenon that arises from the quantum state of the cosmos. Let me try to clarify this with an analogy. Imagine you have a video recording of a sunrise. You can watch it frame by frame, seeing the sun gradually rise above the horizon. Time in this viewing is external to the video. You're watching something that changes as you advance through the frames. But now imagine instead that you have all the frames of the video laid out in front of you simultaneously. You can see the entire sequence at once, from dark sky to full sunrise. In this view, there's no external time. The sense of time comes from the relationships between the frames, from the fact that each frame is slightly different from the ones adjacent to it in the sequence. The Wheeler-DeWitt equation suggests the universe might be more like the second case. The quantum state of the universe would contain all of space at all times in some timeless mathematical structure. What we experience as the flow of time emerges from correlations within this timeless quantum state, much like the sequence of sunrise frames contains the information about temporal progression even when viewed all at once. This idea is both beautiful and deeply strange. It suggests that the universe at its most fundamental level just is. It doesn't evolve or change. All of time, all of history exists simultaneously in the quantum state. The reason we experience time flowing is because we, as conscious observers existing within this quantum state, are correlated with particular configurations of matter and energy, and our memories are encoded in these configurations. We remember the past because our brain states are correlated with earlier states of the universe, creating the psychological arrow of time, even though the fundamental quantum state itself is timeless. Let's explore another aspect of the early quantum universe that's equally mind-bending. In quantum mechanics, there's a fundamental relationship between energy and time that comes from Heisenberg's uncertainty principle. This principle tells us that the uncertainty in energy multiplied by the uncertainty in time must be greater than or equal to a certain minimum value. What this means is that for very short periods of time, energy can fluctuate wildly without violating any physical laws. This has a remarkable consequence. For incredibly brief moments, the quantum vacuum can borrow energy from nowhere, as long as it pays that energy back quickly enough. The shorter the time interval, the larger the amount of energy that can be borrowed. This is how virtual particles pop into and out of existence in the quantum vacuum. They're borrowing energy for such brief moments that nature's accounting system doesn't catch them, so to speak. Now, apply this to the entire universe when it was quantum-sized. The whole cosmos could potentially emerge as a quantum fluctuation, borrowing an enormous amount of energy for an incredibly brief instant. But here's the clever part. If the universe starts expanding rapidly enough during that borrowed time, through something like cosmic inflation, it can actually create the energy it needs to exist through the expansion itself. The gravitational field has negative energy, and as space expands, this negative gravitational energy can balance out the positive energy in matter and radiation, potentially making the total energy of the universe exactly zero. This is a stunning idea. It suggests that the universe might be the ultimate free lunch, as physicist Alan Guth famously put it. The universe could have started as a tiny quantum fluctuation that managed to inflate rapidly enough to become real, creating all its energy from the gravitational field in the process. The total energy of the universe might be zero, with all the positive energy in matter and radiation perfectly balanced by the negative energy in the gravitational field. Let's think about what conditions were like in this early quantum universe from a different angle. When the universe was incredibly small and incredibly dense, everything was packed so tightly that the distinction between matter and energy broke down completely. Einstein's famous equation E equals mc squared tells us that matter and energy are interchangeable, two forms of the same underlying stuff. In the extreme conditions of the very early universe, matter and energy were constantly converting back and forth into each other. At temperatures above a certain threshold, even the identities of particles become fluid. At high enough energies, electrons and positrons, the antimatter counterparts of electrons would be constantly created and annihilated in pairs. Quarks would be free rather than bound into protons and neutrons. Even the fundamental forces of nature, which we experience as distinct phenomena today, would have been unified into a single force. Think about the four fundamental forces we know: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Today, these behave very differently from each other. Gravity is incredibly weak compared to the other forces, but it acts over infinite distances. Electromagnetism is much stronger, but can be attractive or repulsive depending on the charges involved. The strong force holds atomic nuclei together, but only acts over extremely short distances. The weak force governs certain types of radioactive decay and also has a very short range. But in the extreme conditions of the very early universe, these forces were not yet distinct. At energies above about 100 billion electron volts, the electromagnetic force and the weak force merge into a single unified electroweak force. We've actually verified this experimentally in particle accelerators. At even higher energies, still much lower than the Planck energy where quantum gravity effects dominate, the electroweak force and the strong force might unify into a single force, in what's called a grand unified theory. At the Planck energy, if we could somehow reach it, even gravity would presumably unify with the other forces into a single theory of everything. In the first tiny fraction of a second after the Big Bang, the universe was so hot and energetic that it existed in this unified state. There was just one force governing all interactions. As the universe expanded and cooled, this unified force broke down into the separate forces we observe today, somewhat like how water vapor condenses into liquid water when it cools, undergoing a phase transition from one state to another. This process of forces splitting apart as the universe cooled is called symmetry breaking, and it's absolutely crucial to understanding why our universe has the properties it does. Each time a force split off from the unified force, the universe underwent a phase transition that could have profound consequences. These phase transitions might have generated defects in the fabric of space-time, things like cosmic strings or magnetic monopoles, though we haven't detected these exotic objects yet. Now let's think about how the universe transitioned from this quantum state to the classical reality we experience. This is one of the deepest mysteries in quantum cosmology. At some point, the universe had to go from being in a quantum superposition of many possible states to being in one definite classical state. But how did this happen? What caused the quantum universe to collapse into a specific classical history? One possibility is called decoherence. In quantum mechanics, decoherence happens when a quantum system becomes entangled with its environment in such a complex way that it effectively loses its quantum properties and starts behaving classically. Imagine a single particle in a superposition of two locations. As long as the particle remains isolated, it maintains its quantum superposition. But if it interacts with many other particles in its environment, becoming entangled with them in complicated ways, it becomes effectively impossible to observe the quantum superposition. The system behaves, for all practical purposes, as if the particle is in just one location, even though technically the quantum information is still there, just spread out across the environment in an impossibly complex way. For the universe as a whole, decoherence might work similarly. As the universe expanded and cooled, different regions of space would have become entangled with each other in increasingly complex ways. The interactions between different parts of the quantum state would have caused decoherence on large scales, making the universe appear classical, even though at a fundamental level it might still be a quantum superposition. Another perspective comes from the many worlds interpretation of quantum mechanics, originally proposed by physicist Hugh Everett. In this view, the universe never actually collapses from superposition into a single state. Instead, every possible outcome of every quantum event actually occurs, but in separate branches of reality that don't interact with each other. Each time a quantum measurement happens, the universe splits into multiple branches, one for each possible outcome. Applied to cosmology, this means that all the possible quantum states of the early universe actually became real in separate branches of the multiverse. The universe we observe is just one branch where a particular set of quantum outcomes occurred. In other branches, other outcomes happened, potentially leading to universes with very different properties. From our perspective, we see only one history, one set of outcomes, but the full quantum reality includes all possible histories existing in parallel. This many worlds view avoids the measurement problem by denying that collapse ever happens. The quantum state of the universe just evolves according to the Schrödinger equation, continuously splitting into more and more branches as quantum events occur. We perceive only one branch because our consciousness is associated with one particular set of outcomes, but all the other branches are equally real. Different physicists have different views on which of these interpretations is correct, or whether the truth is something else entirely. What's remarkable is that despite this uncertainty about interpretation, quantum cosmology can still make concrete predictions about the early universe that we can test through observations. For instance, the pattern of fluctuations in the cosmic microwave background depends on what was happening in the very early universe. The quantum fluctuations during inflation would have left a specific imprint on these patterns. By measuring the cosmic microwave background with ever greater precision, we're actually probing the quantum state of the universe when it was a tiny fraction of a second old. This is one of the most extraordinary achievements of modern science, that we can observe evidence of quantum mechanics operating on cosmic scales billions of years ago. These observations have confirmed many predictions of inflationary cosmology and quantum mechanics. The fluctuations we see are consistent with quantum fluctuations that were stretched to cosmic scales by inflation. The statistical properties of these fluctuations match what quantum field theory predicts. We're seeing the fingerprints of the quantum universe written across the sky. Another prediction of quantum cosmology concerns gravitational waves from the early universe. Inflation would have produced not just density fluctuations, but also gravitational wave fluctuations, ripples in the fabric of space-time itself that come from quantum fluctuations of the gravitational field. These primordial gravitational waves would have left a subtle imprint on the cosmic microwave background, a particular pattern of polarization that scientists are actively searching for. Detecting this signal would provide direct evidence that gravity itself behaves quantum mechanically and that the universe went through a period of rapid inflation. Let me paint one more picture to help you grasp what the quantum universe was like. Imagine you're trying to take a photograph of something that's moving very quickly. If your camera's shutter speed is too slow, the image comes out blurred because the object moved during the exposure. The photograph doesn't show the object in any single definite location, but rather as a smear across multiple locations. The early quantum universe was similar, but in a more fundamental way. It wasn't that the universe had a definite state that we couldn't quite pin down due to measurement limitations. Rather, the universe genuinely didn't have one definite state. It was a blur of possibilities at the quantum level, and this blurriness was an intrinsic property of reality itself, not just a limitation of our knowledge. As the universe expanded and cooled, this quantum blurriness gradually gave way to classical definiteness, but the process happened gradually rather than all at once. Different aspects of the universe became classical at different times. The large-scale geometry of space might have become classical relatively early, while individual particles remained quantum for much longer. Even today, individual atoms and subatomic particles still exhibit quantum behavior, while large objects like planets and stars behave classically. The transition from the quantum universe to the classical universe wasn't like flipping a switch. It was more like a sunset, where daylight gradually fades into night. There was no single moment when the universe stopped being quantum and started being classical. Instead, quantum effects became less and less important on larger and larger scales as the universe expanded and cooled, until eventually the cosmos took on the familiar classical character we observe today. But here's something profound to consider. Even though we live in what appears to be a classical universe, the quantum nature of reality is still there, lurking beneath the surface. At sufficiently small scales, or under the right conditions, quantum effects still dominate. Every atom in your body, every photon of light entering your eyes right now, every electron flowing through the circuits of whatever device you're using to experience this, all of these behave quantum mechanically. The classical world we perceive is an emergent phenomenon, arising from the average behavior of countless quantum constituents. And when we look out at the largest scales of the universe, at the distribution of galaxies and galaxy clusters stretching across billions of light years, we're seeing structures that ultimately trace their origins to quantum fluctuations in the very first moments of cosmic history. The quantum and the cosmic are intimately connected. The smallest and the largest, the beginning and the present, all linked together in the grand story of quantum cosmology. This brings us to one of the most controversial and fascinating implications of quantum cosmology: the possibility that our universe is not unique. If quantum mechanics allows for multiple possible states, and if the early universe existed in a quantum superposition of possibilities, what happened to all those other possibilities? This question leads us into the realm of the multiverse, a concept that stretches our imagination even further than what we've already explored. Part 4. The Multiverse. Questi mesi can see today. We've journeyed from the ordinary world we experience every day down to the quantum realm and back to the earliest moments of cosmic history. Now, we're going to explore an idea that takes everything we've discussed and multiplies it to an almost incomprehensible degree. We're going to investigate the possibility that our universe, vast and ancient as it is, might be just one bubble in an infinite cosmic foam, just one outcome in an endless sea of possibilities. The multiverse idea emerges naturally from several different lines of reasoning in modern physics, but it connects particularly intimately with quantum cosmology. Let's explore how this connection works and what it might mean for our understanding of reality. Remember that in quantum mechanics, systems exist in superpositions of multiple possible states until measurement occurs. We discussed how, in the early universe, the entire cosmos might have existed in such a superposition, with many possible configurations all simultaneously real at the quantum level. Now, the crucial question is, what happened to all those other possible configurations? In the many worlds interpretation of quantum mechanics, which we touched on earlier, all those possibilities actually became real in separate branches of reality. Every time a quantum measurement occurs, every time a quantum system interacts with its environment in a way that causes decoherence, the universe splits into multiple branches. In each branch, one particular outcome occurred. From inside any single branch, observers like us see only one outcome and perceive that outcome as the definite reality. But all the other branches are equally real, existing in parallel, forever separated from each other. Applied to the early universe, this becomes staggering in its implications. The quantum state of the universe in those first moments contained an enormous number of possible configurations. When decoherence occurred, when the quantum universe transitioned into something classical, all of those possibilities would have spawned separate branches of reality. Each branch would be an entire universe with its own history unfolding from that quantum beginning. In some of these branch universes, the quantum fluctuations during inflation might have played out slightly differently, leading to galaxies forming in different locations. In others, the differences might be more profound. The phase transitions, as forces split apart, might have occurred differently, potentially leading to different values for fundamental constants of nature. Some branches might have more matter than antimatter, while others might have the opposite. Some might have expanded faster, others slower. The number of branches would be truly enormous, perhaps infinite. Every quantum event throughout cosmic history would spawn new branches. The universe, or rather the multiverse, would be an ever-growing tree of possibilities, with branches splitting off branches ad infinitum. Our observable universe, everything we can see with our telescopes stretching across billions of light years, would be just one tiny twig on one branch of this inconceivably vast cosmic tree. But the many worlds multiverse is just one type of multiverse that physicists have discussed. There are several others, each arising from different aspects of fundamental physics. Let's explore the most important types. The first is what's called the quilted multiverse, or the infinite universe. This is actually the simplest type conceptually, and it might exist even without invoking quantum mechanics. If space is truly infinite, extending forever in all directions, and if matter is distributed more or less uniformly on the larger scales, as observations suggest, then there must be other regions of space far beyond what we can see. Our observable universe has a finite size because light has only had a finite time to travel since the Big Bang. We can see out to about 46 billion light-years in any direction, which defines our cosmic horizon. But there's no reason to think space stops there. If space continues infinitely beyond our horizon, then there must be other regions out there, other patches of space, each with their own galaxies, stars and planets. Here's where things get interesting. In any finite region of space, matter can only be arranged in a finite number of ways, albeit an astronomically large finite number. If space is truly infinite, then eventually every possible arrangement of matter must repeat. Somewhere out there, far beyond our cosmic horizon, there must be another region exactly like our observable universe, with an exact copy of you reading these exact words. In fact, there must be infinitely many such copies. This idea seems outrageous, but it follows logically from just two assumptions that most cosmologists accept. Space is infinite, and matter is distributed fairly uniformly on the largest scales. If both are true, then the quilted multiverse exists, and you have doppelgangers scattered throughout the infinite cosmos. The second type of multiverse comes from the theory of eternal inflation. We discussed earlier how inflation, a period of rapid exponential expansion, occurred in the very early universe. But according to many versions of inflation theory, once inflation starts in any region of space, it never completely stops everywhere. In some regions, the inflaton field, the energy field driving inflation, might decay and inflation would end, giving rise to a normal, expanding universe like ours. But in other regions, the field might remain in its high-energy state and inflation would continue. What's more, quantum fluctuations in the inflaton field mean that even in regions where inflation has ended, new inflationary regions can spontaneously appear. This creates a situation where inflation is eternal into the future. Once started, it never completely stops, though it ends in some places while continuing or restarting in others. Each region where inflation ends becomes a separate bubble universe, a pocket universe with its own Big Bang and its own subsequent history. These bubble universes expand within the eternally inflating background like bubbles forming in a pot of boiling water. Each bubble is causally disconnected from the others, meaning no signal or influence can travel from one bubble to another. Each bubble is effectively a separate universe. The remarkable thing about eternal inflation is that it generates an infinite number of these bubble universes, each potentially with different properties. The way the inflaton field decays might be different in different bubbles. The phase transitions that occurred as forces split apart might play out differently. Each bubble universe might have different values for the fundamental constants of nature, different particle physics, potentially even different numbers of spatial dimensions. This brings us to a crucial concept called the landscape of string theory. String theory, one of the leading candidates for a theory of quantum gravity, suggests that all particles and forces arise from tiny vibrating strings. The mathematics of string theory requires extra dimensions of space beyond the three we experience. These extra dimensions are thought to be curled up into complex geometrical shapes, so small we don't notice them. Here's the key insight. There are an enormous number of different ways these extra dimensions could be curled up, each giving rise to different physics in the three large dimensions we experience. Physicists estimate there might be something like 10 to the power of 500 different possible configurations, each corresponding to a different vacuum state with different properties. In the context of eternal inflation, different bubble universes might settle into different vacuum states from this vast landscape of possibilities. Each bubble would have physics determined by which vacuum state it ended up in. The constants of nature, like the strength of gravity or the mass of the electron, would be different in different bubbles. Some bubbles might have physics very different from ours, perhaps with no atoms or with forces that prevent structures from forming. This leads us to one of the most contentious ideas in modern physics, the anthropic principle. The anthropic principle, in its weak form, simply states that we should not be surprised to observe the universe having properties compatible with our existence, because we obviously couldn't exist in a universe with properties that don't allow for observers. Here's why this becomes relevant for the multiverse. Our universe seems to be fine-tuned for life in various ways. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If it were slightly weaker, stars might never form at all. If the strong nuclear force were a bit different, atomic nuclei couldn't exist. If the cosmological constant, the energy of empty space that's causing the universe's expansion to accelerate, were much larger, galaxies could never have formed because space would have expanded too quickly. For decades, physicists puzzled over this apparent fine-tuning. Why do the constants of nature have the specific values they do, values that seem precisely calibrated to allow complex structures and ultimately life to exist? Some saw this as evidence for a designer or a deep underlying principle that requires these specific values. The multiverse offers a different explanation. If there are countless universes with different values for the fundamental constants, then it's no surprise that we find ourselves in one of the rare universes where the constants allow for stars, planets, and life. We couldn't possibly find ourselves anywhere else. all the other universes with different constants still exist, but they're uninhabited because they can't support observers. This is the anthropic explanation for fine-tuning. The constants have the values we observe, not because they must have those values, but because we can only exist in the tiny subset of universes where they do. This reasoning is controversial for several reasons. Some physicists argue that it's not really an explanation at all, that it gives up on finding deeper principles that would actually predict the values of constants from first principles. Others worry that the multiverse can explain anything and therefore explains nothing, that it's unfalsifiable and therefore not really scientific. Still, others embrace it as the most natural interpretation of both quantum mechanics and modern cosmology, a picture that emerges inevitably from our best theories. There's yet another type of multiverse worth mentioning, sometimes called the mathematical multiverse. The physicist Max Tegmark has proposed that every logically consistent mathematical structure exists as a physical reality. Our universe would be just one such mathematical structure, one set of equations and initial conditions. But all other possible mathematical structures would also exist as separate universes with their own laws of physics, perhaps even with different logics or different fundamental ontologies. This is perhaps the most radical multiverse proposal of all. It suggests that not only are there other universes with different constants and particle physics, but there are universes with entirely different mathematical structures underlying them, universes that might be so alien to our way of thinking that we couldn't even comprehend what existence means in those contexts. Let's step back and think about what all these multiverse ideas mean. If any version of the multiverse is correct, then the cosmos is vastly larger and more diverse than we ever imagined. Our observable universe, everything we can see with our telescopes, would be an infinitesimally tiny fraction of what exists. All of human history, all the galaxies we've observed, all the stars and planets in our cosmic neighborhood would be just one local patch of reality in an infinite tapestry. This has profound implications for how we think about our place in the cosmos. The Copernican revolution taught us that Earth is not the center of the universe, that we orbit an ordinary star in an ordinary galaxy. The multiverse takes this further. Not only is our planet unremarkable, not only is our galaxy one among billions, but our entire universe might be one among infinitely many. We would be living in what could be called a level of insignificance beyond what anyone before the 21st century could have conceived. Yet there's another way to view this. If the multiverse exists, then reality is far richer and more magnificent than we imagined. The fact that all these possibilities exist, that quantum mechanics and inflation and the mathematics of string theory lead naturally to this infinite proliferation of universes, reveals something profound about the creative power of physical law. The universe, or multiverse, is not parsimonious. Given the possibility of existence, reality goes all out, actualizing every possibility that physics allows. Some physicists and philosophers worry about the implications of the multiverse for scientific explanation. If anything that can happen does happen in some universe, then it seems we can't make predictions or explain why things are the way they are in our universe. Everything becomes possible, and therefore everything becomes equally unexplained. But defenders of the multiverse argue that we can still make predictions, just probabilistic ones. We can ask, given that we exist as observers, what should we expect to observe in our universe? This leads to calculations about which types of universes are most likely to contain observers, and therefore which properties we should most likely observe. Some versions of multiverse theory make testable predictions about things like the cosmic microwave background or the distribution of matter that can be compared with observations. The question of whether the multiverse is science or speculation remains hotly debated. Unlike theories about particles or forces that we can test in laboratories, we can never directly observe other universes. If they exist, they're causally disconnected from us, separated by infinite distances, or existing in separate branches of quantum reality that don't interact. Does this mean the multiverse is forever beyond the reach of science? Many physicists argue that the multiverse should be judged not as a standalone theory, but as a consequence of other theories that we can test. We can test inflation, quantum mechanics, and string theory through their predictions about things we can observe in our universe. If these theories are confirmed and they inevitably lead to the multiverse, then we have indirect evidence for the multiverse, even if we can never observe other universes directly. Think of it this way. We can't directly observe the interior of a black hole either, because no information can escape from inside the event horizon. Yet we're confident black holes exist because we observe their effects on surrounding matter and because they're a firm prediction of general relativity, which is well tested in other contexts. Similarly, other universes might be unobservable, but if they're inevitable consequences of well-tested theories, we might have good reason to believe they exist. The multiverse also touches on questions that go beyond physics into philosophy and even theology. If all possible universes exist, what does this mean for meaning and purpose? If everything that can happen does happen somewhere, what makes any particular outcome significant? If there are infinite versions of you making different choices in different universes, what does that mean for free will and moral responsibility? These are deep waters, and physics alone cannot provide all the answers. But what's remarkable is that quantum cosmology and the multiverse ideas it naturally leads to have forced these ancient philosophical questions into the realm of scientific discussion. Questions about the nature of existence, why there is something rather than nothing, and what it means to be a conscious observer in the cosmos have become, at least in part, scientific questions that we can approach with mathematical models and empirical observations. Whether the multiverse exists remains an open question. It might be that future developments in fundamental physics will point clearly to one type of multiverse or another. Or it might be that more refined theories will show the multiverse is unnecessary, that there are deeper principles that explain why our universe has the properties it does without invoking an infinite number of other universes. Only time and continued research will tell. What's clear is that quantum cosmology has opened up these possibilities, has shown us that our best theories naturally lead to ideas that would have seemed like pure fantasy just decades ago. The quantum nature of the early universe, the way it existed in superposition with multiple possible configurations, connects intimately with these multiverse concepts. Whether or not other universes literally exist, the mathematics of quantum cosmology describes them, and that fact alone tells us something profound about the nature of reality. Part 5. What this means for everything. We've traveled through an extraordinary intellectual landscape, from the familiar world of everyday experience down to the quantum realm, back to the first moments of cosmic history, out to the possibility of infinite other universes. And now we're going to bring all of this together and explore what it means. What does quantum cosmology tell us about the biggest questions humans have ever asked? Let's start with perhaps the most fundamental question of all. Did time have a beginning? This question has occupied philosophers and theologians for millennia. Common sense suggests that either time stretches back infinitely into the past, or there was a first moment when time began. Both possibilities seem deeply problematic. If time had no beginning, then an infinite amount of time has already passed, which seems paradoxical. But if time had a beginning, what could possibly have caused that beginning, since causes themselves seem to require time? Quantum cosmology offers a way out of this dilemma that neither philosophy nor classical physics could provide. As we discussed with the Hawking-Hartle no-boundary proposal, time might not have a beginning in the traditional sense, because time itself might gradually transform into something space-like as we approach what would classically be called the Big Bang. The question, what came before the Big Bang, becomes meaningless, not because there's a barrier preventing us from looking further back, but because the concept of before ceases to apply. Think about this carefully. We're so used to thinking of time as something fundamental, something that just exists as a stage on which events play out. But quantum cosmology suggests time itself might be an emergent phenomenon, something that arises from deeper quantum structures. In the most fundamental description of reality, time might not even be a meaningful concept. What we experience as the flow of time might be more like a rainbow, a real phenomenon that emerges from underlying processes but that doesn't exist as an independent thing in itself. This has profound implications. If time is emergent, then asking what caused the Big Bang might be like asking what caused time itself. But causation requires time, requires that one event come before another. If time emerged along with space from some timeless quantum state, then the whole framework of cause and effect might not apply to the origin of the universe itself. Some physicists and philosophers have suggested that the universe might be self-caused in a quantum mechanical sense. In quantum mechanics, things can happen without causes in the classical sense. Quantum events are fundamentally probabilistic. A radioactive atom decays at some particular moment, but there's no cause for why it decayed at that moment rather than another. It just happens, with a certain probability governed by quantum mechanics. Perhaps the universe is similar. Perhaps it simply popped into existence through a quantum process, not caused by anything, but not violating any physical laws either. The laws of quantum mechanics would describe the probability for this to happen, but wouldn't point to any cause in the traditional sense. This is deeply unsettling to many people, because it seems to violate one of our deepest intuitions, that everything must have a cause. But quantum mechanics has already shown us that this intuition fails at the microscopic level. Quantum cosmology suggests it might fail at the cosmic level too. This brings us to another ancient question. Why is there something rather than nothing? This question has been called the deepest of all mysteries. The fact that anything exists at all seems to call out for explanation. Yet any explanation seems to presuppose something already exists, whether it's physical laws, God, or some other foundation. Quantum cosmology offers some tantalizing hints about this question, though not a complete answer. We've discussed how the universe might have tunneled into existence from nothing through a quantum process. But what exactly is meant by nothing in this context? In quantum field theory, even a perfect vacuum, completely empty space, is not truly nothing. It's a seething foam of quantum fields, constantly fluctuating, with virtual particles popping in and out of existence. So when physicists talk about the universe coming from nothing, they often mean coming from this quantum vacuum, not from absolute philosophical nothingness. But where did the quantum fields come from? Where did the laws of quantum mechanics come from? Some physicists, like Lawrence Krauss, argue that this quantum vacuum is the most refined notion of nothing that makes sense physically, and that trying to explain existence starting from some more absolute form of nothingness is asking physics to answer a question outside its domain. Others, including many philosophers, argue that this doesn't really answer the question. The quantum vacuum with its fields and laws is definitely something, not nothing. The question of why there are laws of nature at all, why there is a quantum vacuum rather than absolutely nothing, remains unanswered. Perhaps the question itself is somehow misformed. Perhaps existence is in some sense necessary, the only coherent possibility, though we don't yet understand why. Or perhaps, in the context of the multiverse, all possible laws and all possible types of universes do exist. And the question becomes not why there is something rather than nothing, but why is existence so profligate, actualizing every mathematical possibility? These deep metaphysical questions connect to another aspect of quantum cosmology that we should explore: the role of consciousness and observation. In ordinary quantum mechanics, the measurement problem looms large. What causes the quantum state to collapse from superposition into one definite outcome? Different interpretations give different answers, but many involve the role of observers or measurement in some fundamental way. When we scale this up to quantum cosmology, the questions become even more perplexing. If the early universe existed in a quantum superposition, what caused it to collapse into one definite history? There was no observer external to the universe to make a measurement. Does this mean consciousness played some role in actualizing the classical universe from quantum possibilities? Some physicists, like John Wheeler with his participatory universe idea, have suggested that observers play a fundamental role in bringing the universe into being. In this view, the universe is not fully real until it is observed, and conscious observers are necessary to give reality its concrete character. This leads to a kind of cosmic bootstrap, where the universe creates conditions for observers to arise, and observers in turn actualize the universe by observing it. This idea has a kind of poetic appeal, but most physicists are skeptical that consciousness plays such a fundamental role. More likely, decoherence through purely physical interactions is sufficient to make the universe classical, without needing to invoke consciousness. The environment itself can serve as an observer of sorts, with different parts of the universe entangling with each other in ways that produce classical behavior. Still, the connection between quantum mechanics and consciousness remains mysterious. We don't understand how conscious experience arises from physical processes in the brain, and we don't understand why quantum mechanics seems to give a special role to measurement and observation. These might be connected mysteries, or they might be separate puzzles that just happen to both involve subjective experience and physical reality in confusing ways. Let's think about what quantum cosmology tells us about the arrow of time, the fact that time seems to flow in one direction. We remember the past, but not the future. Eggs break, but don't spontaneously reassemble. Heat flows from hot to cold, but not the reverse. This asymmetry seems fundamental to our experience, yet the microscopic laws of physics are almost entirely symmetric in time. You could run a movie of fundamental particle interactions backward, and it would look just as physically valid. The arrow of time is usually explained by entropy, the second law of thermodynamics that says disorder tends to increase. But this just pushes the question back. Why was entropy low in the past? Why did the universe start in a highly ordered state that has been becoming more disordered ever since? Quantum cosmology might offer an answer. The very early universe, despite being incredibly hot and energetic, was actually in a very low entropy state because it was extremely uniform. There were only tiny fluctuations from place to place. As the universe expanded and cooled, gravity amplified these tiny differences, pulling matter together into clumps that eventually became galaxies and stars. This process of structure formation increased entropy enormously. Why did the universe start in such a low entropy state? This might be connected to the quantum origin of the universe. The quantum state that tunneled into existence or emerged from the no-boundary proposal might have had special properties that naturally gave rise to a low-entropy beginning. The arrow of time, the fact that we experience time flowing in one direction, might ultimately be explained by quantum cosmology's description of how the universe began. There's another profound implication of quantum cosmology that we should consider: what it tells us about the limits of knowledge. There seem to be fundamental barriers to what we can know about the universe. The cosmic horizon limits how far we can see because light from more distant regions hasn't had time to reach us. The Planck scale seems to represent a fundamental limit on how finely we can probe space and time. Quantum indeterminacy means we cannot know certain properties with perfect precision simultaneously. These aren't just practical limitations that better technology might overcome. They appear to be fundamental features of reality itself. Quantum cosmology suggests that there might be questions about the universe that have no answer. Not because we're not clever enough to find the answer, but because the questions themselves don't correspond to anything real. Asking what happened before the Big Bang might be such a question if time itself emerged at the Big Bang. This represents a kind of epistemic humility that science is learning to embrace. For much of the history of science, there was an assumption that given enough time and resources, we could eventually understand everything about the universe. But quantum cosmology, along with other developments in modern physics, suggests that reality might be more subtle than that. There might be aspects of existence that are fundamentally beyond our ability to observe or even conceptualize. Yet, despite these limitations, quantum cosmology has given us extraordinary insights. We can talk meaningfully about what the universe was like when it was a billionth of a billionth of a billionth of a second old. We can trace the origin of galaxies back to quantum fluctuations smaller than an atom. We can calculate probabilities for different histories of the entire cosmos. This is an almost miraculous achievement of human intellect. Think about the tools we've used to reach these insights. Mathematics, observation, and human reason have allowed us to peer back to the very edge of time, to understand the behavior of the entire universe when it was quantum-sized. We've never been to those early moments. We can never repeat the experiment of cosmic creation. We can't hold the early universe in a laboratory or examine it directly. Yet, through the power of mathematics and the evidence encoded in the cosmic microwave background and the large-scale structure of the universe, we've reconstructed what happened with remarkable confidence. This speaks to something profound about the relationship between mind and cosmos. The universe is comprehensible to us. The mathematics that describes quantum fields and curved space-time, abstractions created by human minds, actually capture something true about physical reality. This unreasonable effectiveness of mathematics, as physicist Eugene Wigner called it, remains one of the deepest mysteries. Why should the universe be mathematical in structure? Why should equations scribbled on paper or coded into computers correspond so precisely to the behavior of reality? Some physicists and philosophers have suggested that this is not really surprising, because we're part of the universe ourselves. Our minds evolved within this cosmos, shaped by the same laws that govern everything else. Perhaps our mathematics is effective because our brains are physical systems that resonate with the mathematical structure of reality. We're not external observers trying to understand an alien system. We're the universe trying to understand itself. This brings us back to a theme that's woven throughout quantum cosmology: the interconnection of observer and observed, the way consciousness sits within the physical cosmos yet somehow can comprehend it. We are arrangements of atoms that were forged in stars, collections of particles governed by quantum mechanics, patterns of matter and energy that arose from quantum fluctuations in the early universe. Yet we can understand these origins. We can trace our own history back to the Big Bang. We can comprehend, at least partially, the quantum processes that gave birth to everything. There's something almost miraculous about this. The universe began in a state we can barely imagine, a quantum superposition of possibilities, incredibly tiny and incredibly simple. Through 14 billion years of evolution, guided by the laws of physics, that initial state gave rise to stars and planets, and eventually to structures complex enough to be aware, to wonder about their origins, to do the mathematics and observations necessary to reconstruct their own history. The cosmos has become self-aware through us. Some philosophers and scientists have speculated that this might not be an accident. Perhaps the universe must give rise to observers in order to actualize itself from quantum possibility into classical reality. Perhaps consciousness is not an incidental byproduct of cosmic evolution, but somehow built into the structure of existence itself. These ideas remain speculative and controversial, but quantum cosmology at least makes them discussable within the framework of physics. Let's think about what quantum cosmology suggests about the future of the universe. We've focused mainly on origins, but the quantum nature of the cosmos also has implications for its ultimate fate. Current observations suggest the universe will expand forever, with expansion actually accelerating due to dark energy, the mysterious energy that fills empty space. Galaxies will move farther and farther apart. Stars will eventually burn out. Black holes will evaporate through Hawking radiation. In the unimaginably distant future, perhaps 10 to the 100 years from now, the universe might consist of nothing but isolated particles drifting through an ever-expanding void. But quantum mechanics introduces uncertainty even into this far future. Quantum fluctuations never completely stop. Even in the far future, there's a tiny probability that a new inflationary region could spontaneously form, giving birth to a new bubble universe. The cosmos might be cyclic in some sense, with new beginnings emerging from quantum processes, even in what seems like the death of the old universe. Some versions of quantum cosmology even suggest that time might be cyclic, that the universe might undergo endless cycles of expansion and contraction, or that what we call the Big Bang might have been a quantum transition from a previous phase of the universe rather than an absolute beginning. These ideas remain speculative, but they show how quantum cosmology opens up possibilities that classical cosmology could never have conceived. What about the practical implications of quantum cosmology? Does understanding the quantum origin of the universe have any relevance to our everyday lives? In one sense, the answer might seem to be no. Whether the universe tunneled into existence from nothing or emerged from a no-boundary state makes no difference to how we live our daily lives, how we treat each other, or what gives our lives meaning and purpose. But in another sense, quantum cosmology represents one of the greatest achievements of human culture, comparable to great works of art or literature or philosophy. It's part of humanity's ongoing attempt to understand our place in the cosmos, to answer the fundamental questions about existence that have occupied every culture throughout history. These questions matter because they're part of what makes us human. We are creatures who wonder about where we came from and why we're here. Moreover, the technologies that emerge from quantum mechanics have transformed our world. Computers, lasers, medical imaging devices, GPS systems all depend on our understanding of quantum physics. The same kind of fundamental research that's pushing into quantum cosmology might eventually lead to technologies we can't currently imagine. History shows that understanding the deepest workings of nature often pays practical dividends, though usually in ways we don't anticipate. There's also something profound about the unity of knowledge that quantum cosmology represents. It connects the smallest scales to the largest, links the beginning of time to the present moment, bridges theoretical physics and observational astronomy, touches on philosophy and even theology. It shows that human knowledge forms an interconnected web, where insights in one domain illuminate others in unexpected ways. As we think about what quantum cosmology means for everything, we should also consider what it suggests about the value of knowledge itself. We live in an age where practical utility is often valued above pure understanding. But quantum cosmology reminds us that some questions are worth pursuing simply because they're deeply human questions, because the desire to understand is part of what makes us who we are. The universe didn't have to be comprehensible. It could have been utterly chaotic, following no discernible patterns or laws. Or it could have been so complex that no finite minds could grasp its workings. But instead, we find ourselves in a cosmos that, while extraordinarily strange at its deepest levels, follows mathematical laws that we can discover and understand. This fact itself seems worthy of wonder. Quantum cosmology also teaches us about the importance of being willing to follow ideas wherever they lead, even when they challenge our intuitions or lead to conclusions that seem absurd. The idea that the entire universe was once smaller than an atom seems ridiculous. The notion that reality exists in quantum superposition seems to violate common sense. The possibility of infinite other universes seems like pure science fiction. Yet these ideas emerge naturally from our best theories when we apply them rigorously and honestly. This willingness to accept conclusions that follow from evidence and mathematics, even when they conflict with intuition, is one of science's greatest strengths. It's led us to understand things that would have seemed impossible to previous generations. It's taken us from thinking Earth was the center of everything to understanding that we live on one planet, orbiting one star in one galaxy among billions, in a possibly infinite cosmos that might itself be just one of countless universes. Each step in this journey has made the universe seem larger and stranger, and has made our place in it seem both smaller and more remarkable. We're tiny, living on a speck of dust in an incomprehensibly vast cosmos. Yet we're also extraordinary, perhaps the only structures in our cosmic neighborhood complex enough to understand where we came from and how we got here. Conclusion: the universe's ongoing mystery. We've journeyed together through one of the most profound intellectual adventures in human history. We've explored how the universe began, what it was like when it was quantum-sized, how quantum fluctuations became galaxies, and what all of this means for the deepest questions we can ask about existence itself. Now, as we reach the end of our exploration, let's reflect on where this leaves us. Quantum cosmology has given us remarkable insights into cosmic origins. We understand that the Big Bang was not an explosion in space, but an explosion of space itself. We know that in the earliest moments the universe was governed by quantum mechanics, existing in a superposition of possibilities before settling into the definite classical reality we observe today. We've traced the structures we see around us, from galaxies to planets to the atoms in our bodies, back to quantum fluctuations that occurred when the universe was incomprehensibly tiny and young. Yet, for all we've learned, profound mysteries remain. We still don't have a complete theory of quantum gravity that fully reconciles general relativity with quantum mechanics. We don't know for certain whether the multiverse exists or whether our universe is all there is. We don't fully understand how the quantum universe transitioned to a classical one, or what role, if any, consciousness plays in that transition. We don't know whether time had an absolute beginning, or whether it emerges from something more fundamental. These unanswered questions aren't failures of quantum cosmology. They're invitations to future discovery. Science never claims to have all the answers. What makes science powerful is not that it provides certainty, but that it provides a rigorous method for refining our understanding, for getting progressively closer to truth, even if we never reach absolute certainty. The story of quantum cosmology is still being written. Right now, telescopes are mapping the cosmic microwave background with ever greater precision, searching for the subtle patterns that would confirm inflation and reveal details about the earliest moments of cosmic history. Physicists are working on theories of quantum gravity, trying to find a framework that consistently combines quantum mechanics with general relativity. Mathematicians are exploring the implications of various quantum cosmology models, calculating what we should observe if different scenarios are correct. Each new observation, each theoretical advance, adds another piece to the puzzle. Sometimes these pieces confirm what we expected. Other times they surprise us, forcing us to revise our understanding in ways we didn't anticipate. This is the exciting reality of working at the frontier of human knowledge. We're not just learning facts about a static cosmos. We're discovering that the universe is stranger and more wonderful than we imagined, and each answer we find raises new questions we hadn't thought to ask. Consider what we now know that would have seemed like magic or madness to people living just a century ago. We know the universe had a beginning roughly 14 billion years ago. We know it's been expanding ever since, and that this expansion is actually accelerating. We know that galaxies are rushing away from us and from each other as space itself stretches. We know that the elements in our bodies were forged in the hearts of stars that exploded long before the sun was born. We know that quantum mechanics governs the behavior of atoms and subatomic particles, and that these quantum rules somehow applied to the entire universe when it was newborn. A century from now, what will we know that would seem equally fantastic to us today? Perhaps we'll have a complete theory of quantum gravity. Perhaps we'll have definitive evidence for or against the multiverse. Perhaps we'll understand how consciousness arises from physical processes and what role it plays in quantum mechanics. Perhaps we'll have answered the question of why there is something rather than nothing. Or perhaps we'll have understood that the question itself needs to be reformulated in ways we can't currently conceive. What's certain is that the quest to understand will continue. This quest is part of what makes us human. We're creatures who look up at the night sky and wonder. We're not content to simply exist. We want to understand where we came from, how we got here, what it all means. This drive to comprehend has taken us from early humans telling myths around fires to modern scientists probing the first moments of cosmic history with mathematics and telescopes. Quantum cosmology sits at the intersection of our smaller scale physics and our larger scale questions. It connects the quantum realm to the cosmic scale. It links the beginning of time to the present moment. It shows us that the universe has a history, that it evolved from a state radically different from what we see today, and that this evolution followed laws we can discover and understand. There's something deeply satisfying about this understanding, even though it leaves mysteries unsolved. We may not know everything, but we know something real and profound about where we came from. We understand the broad outlines of cosmic history from a tiny fraction of a second after the Big Bang to the present day. We've traced our own origins back through billions of years of evolution, through the formation of Earth and the Sun, through the creation of the Milky Way galaxy, through the era when the first stars formed, all the way back to quantum fluctuations in the initial moments of cosmic inflation. This is a story of almost mythic grandeur, yet it's grounded in mathematics, observations, and careful reasoning. It's a creation story for the scientific age, one that doesn't require us to abandon reason or evidence, yet one that fills us with wonder at the magnificence and strangeness of existence. Quantum cosmology also reminds us of the power of human cooperation across time and space. The understanding we have today was built by thousands of scientists across many generations and many countries. Each contributed pieces to the puzzle. Einstein gave us general relativity. Hubble showed us the universe is expanding. Gamow, Alpha and Hermann predicted the cosmic microwave background. Penzias and Wilson discovered it. Guth proposed inflation. Hawking and Hartley developed the no-boundary proposal. Countless others contributed observations, calculations, and insights that gradually assembled into our current picture. This is how science works at its best, as a collective human endeavor where knowledge accumulates across generations, where researchers from different backgrounds and nations collaborate to understand truths that transcend any individual or culture. The story of quantum cosmology is a reminder that when we work together in pursuit of understanding, we can achieve things that would be impossible for any individual or single generation. As you think about what we've explored together, I hope you feel some of the wonder that physicists feel when contemplating these ideas. The universe is strange beyond imagining, yet comprehensible through mathematics and observation. It had a beginning that involved quantum processes we're still working to fully understand. It evolved from incredible simplicity to create galaxies, stars, planets, and eventually life and consciousness. And now, 14 billion years after it began, parts of the universe have become capable of understanding their own origins. You are made of stardust, as Carl Sagan famously said. But it's even more remarkable than that. You're made of particles that were once compressed into a volume smaller than an atom. You're made of matter that went through quantum fluctuations in the earliest moments of cosmic history. The atoms in your body have been on a 14 billion year journey from the Big Bang to this present moment. You are the universe experiencing itself, asking questions about its own nature. Quantum cosmology is more than just a scientific theory. It's a profound story about existence itself, about how something emerged from what might have been nothing, about how simplicity gave rise to complexity, about how blind physical laws created a cosmos capable of producing minds that can understand those very laws. It's a story that's still unfolding, with new chapters being written by scientists working right now to push the boundaries of human knowledge a little further. The mysteries that remain are not reasons for despair, but reasons for excitement. They're opportunities for future discoveries, invitations for the next generation of scientists and thinkers to push our understanding deeper. Perhaps some of you experiencing this will be part of that next generation, contributing to our evolving understanding of cosmic origins. Whether or not you pursue physics professionally, I hope you carry with you a sense of wonder at the magnificent cosmos we inhabit. The universe is far stranger and more beautiful than everyday experience suggests. Beneath the familiar surface of ordinary life, there's a quantum realm where particles exist in superposition and uncertainty reigns. Beyond our cosmic horizon, there might be infinite other regions of space or even entirely separate universes. And in our past, there's a moment when everything that exists was compressed into something smaller than we can imagine. Existing in a quantum state we're only beginning to understand. This is our cosmic heritage. This is where we came from. And the fact that we can know this, that we can trace our origins back to the first moments of time through careful observation and rigorous thinking, is perhaps as remarkable as the origins themselves. The universe has given birth to minds capable of comprehending it, and we're living in an extraordinary time when that comprehension is advancing rapidly. So look up at the night sky with new understanding. Those stars are glimpses into the past, their light traveling for years or centuries before reaching your eyes. They're made of the same elements you are, forged in similar nuclear furnaces. Those distant galaxies rushing away from us reveal the expansion of space itself, and in the faint glow of the cosmic microwave background, invisible to your eyes but detectable with the right instruments, there's the afterglow of the Big Bang itself. Photons that have been traveling for nearly 14 billion years, carrying information about the universe when it was just a few 100,000 years old. You live in a quantum universe, one that began in a state we're still trying to fully comprehend, one that evolved according to laws we can discover and understand. You're part of an unbroken chain of causation, stretching back to the very beginning, connected to every other part of the cosmos through shared history and shared physical law. And you have the remarkable privilege of living at a time when humanity is uncovering these deep truths about existence. The journey of quantum cosmology continues. New telescopes will peer deeper into space and time. New theories will be proposed and tested. New questions will emerge that we haven't yet thought to ask. The story of cosmic origins is far from complete. But what we've learned already is extraordinary, and what we'll learn in the decades and centuries ahead promises to be even more remarkable. So embrace the mystery. Marvel at what we've discovered. Stay curious about what remains unknown. And remember that you're not separate from this cosmic story. You're part of it. You're aware that the universe has become conscious of itself, a pattern of matter and energy complex enough to wonder about its own origins and destiny. In that sense, when you contemplate the quantum origin of the universe, you're not an outside observer studying a foreign object. You're the cosmos contemplating itself, and there's profound beauty in that realization. The universe's journey from quantum uncertainty to classical reality, from a state smaller than an atom to the vast cosmos we observe today, is the greatest story ever told. And it's a true story grounded in evidence and mathematics, confirmed by observations across the electromagnetic spectrum, tested through decades of careful scientific work. It's a story that connects the smallest to the largest, the earliest moments to the present day, matter to energy, space to time, and ultimately connects us to everything that exists. Welcome to the quantum universe. Welcome to the cosmos that quantum cosmology reveals. It's stranger, vaster, and more wonderful than anyone could have imagined, and we've only just begun to explore its mysteries. The adventure continues, and in some small way, by learning about these ideas, by grappling with these concepts, by letting yourself feel wonder at the magnificence of existence, you become part of that adventure. You become part of humanity's ongoing quest to understand the cosmos and our place within it. And that, perhaps, is the ultimate meaning that quantum cosmology offers. We're not just passive inhabitants of a universe we don't understand. We're active participants in a grand endeavor to comprehend reality itself. The quantum foam that existed at the beginning has given rise to minds capable of understanding quantum mechanics. The universe has become self-aware, and through that self-awareness, it continues to discover its own nature. This is the extraordinary legacy of 14 billion years of cosmic evolution, and this is the profound gift that quantum cosmology has given us. A scientifically grounded understanding of where everything came from, how it all began, and how we came to be here to ask these questions in the first place. The quantum universe is your universe. Its story is your story, and the ongoing quest to understand it more deeply is humanity's story. May you carry forward with you a sense of wonder at this magnificent cosmos and an appreciation for the remarkable fact that we can understand it at all.